ways. It's like all of a sudden you realize, oh, this is happening. I wouldn't have thought of that. So for example, we've seen, the instruments tell us that there might be some melt at a station. So why aren't the streams running much more full? So for example, we're on one of the glaciers, Taylor Glacier, and we're walking along, and we actually saw some melt. And it was just a little layer of water kind of bleeding over the surface as if somebody had just spilled a drink. But it got to a certain point where apparently the wind regime was a little bit different because the roughness of the glacier was a little bit different. It stopped and it froze in place. So if our MET station was at the origin of the water, it would have told us it was melting. And then 10 feet away, it froze. And that's not where our MET station is. So it kind of helps to kind of see this. So when we do our modeling of the glacier surface, we're a lot more aware of the subtleties that could happen.
Do you think there'll ever be instrumentation that can take into account all of these subtleties, or it's just something about, unless it's just something about being a human being and being able to experience this stuff?
This is the fundamental argument that NASA's had since its inception.
Right.
Do you want to put a guy in space at great cost, or can you just send up a satellite and do the same thing? Well, depending on what you want to do, you don't want to keep a human circling the Earth taking pictures, for 20 years. A satellite's great at doing that. But to kind of see what the condition of the Earth is, or have a visceral feel of what the surface of the moon is, maybe it's worth the expense to do that. So we're kind of in the same boat. But having said that, there is a cost-effective approach to automating a lot of our instruments. So for example, rather than, right now the way our instruments work is you have to go to the weather station, and then you have to download the data, you have to take the can, and that's a good thing in the sense that it makes us check out the station and see how it's doing. But we could reduce our visits by half, say, if it would be telemetered. If we send it out by satellite.
Yeah,
because
like the AWS station.
Right. It's not, in this case, it's not so much the problem of the sensor tilting, but in this case, it's the situation of the MET station falling over. Because it's happened before. A big windstorm comes, the station falls over. Then we would know we would have to make a special visit so we don't lose a lot of data, or we just visit once a year, and if all the instruments look fine, great, we'll just come back next year and not come back again the same year.
Right.
So that kind of thing would really help out a lot.
And okay, where was it? So now you're going to be overseeing the whole LTER.
Yeah, that's right.
System coming soon. And what is the entire LTER? What is that consider? That's more than just Antarctica. It's
well, no.
You'll be overseeing the Antarctic area.
Yeah. The Long-Term Ecological Research Program has 26 sites, 24 of which are in the U.S.
Wow.
Alaska has 2, Oregon has 1, California might have 2 or 3, Colorado has 2, Michigan has 1. So there's a lot of these sites, and then Antarctica has 2. One on the peninsula, the Antarctic Peninsula at Palmer Station, and they're basically an Antarctic marine-based project. And then the other one is us here, where we're an Antarctic terrestrial-based project. So I'll only be taking over our project here in the Dry Valleys.
Okay, which involves, what's the scale of something like that?
Well, it involves 8 universities and 8 scientists from different universities, and it's basically managing the budget and trying to focus the resources on whatever problem or focus we choose in this coming year. Because we're limited by resources, not everybody can come here and do what they want. We have to say, okay, what are our choices? What's most important to do this year? We have core measurements, like the glaciers and the weather. There's others in the lakes and the streams. So we have those core measurements. And then we have resources left over in terms of helicopter time and allowing people to come into Antarctica. And then we divvy those up according to what we want to do from year to year. So for example, Peter Norn, you talked to him before, if he has a dive season where he's looking at the algal mats in the bottom of the lake, so he needs a lot of people to do that.
Yeah.
So those resources have to be drawn from other projects. So he can't do that every year, but he does it every so often. And then the rest of our projects, like mine, for example, I might have fewer people in the field that year as we kind of help him, or conversely, he helps me some other year.
When you talk about the core measurements, you're talking about the LT part of the LTER, the
Right.
idea, and can you explain that a little bit? What is so important about this being a long-term project? What's special about that?
Well, the typical National Science Foundation project, and for that matter, the NASA project, is on 3-year cycles. So you propose your project, if you get funded, then you have 3 years to do what you need to do. And that's fine for a lot of things. If you want to understand, say, for example, how a glacier flows, and you're just trying to look at the basic mechanics of that, maybe 3 years is sufficient to figure that out. But in our system, where we're looking really at ecological responses to meteorological or climate forcing, it's really important to look at this over the long term, because we don't know what the weather is going to be or what the weather might do. So, for example, not using our site as an example, but let's use the one in Puerto Rico. Their system is dominated by hurricanes that come through and devastate the forests, and then the ecosystem responds to that. So if you have a 3-year project, that doesn't mean you're going to get a hurricane through that time period. And say you do get a hurricane through that time period, well, you might not have enough funding to see the complete response of the system to that catastrophic event. For us, for example, our catastrophic or our big event is this melt year that you might have heard of.
Oh yeah, when was that?
That was 2001.
Okay, yeah.
And that's when the temperature actually went up to 4 degrees C. So what's that? You know, like 35 degrees for 3 weeks. So it wasn't
Wow.
like all summer. It was like 3 weeks. There's water all over the place, and so we're able to catch that because we have a long-term project, and then we could follow the response of the system to that. So in our system, that was increased sediment flow to the lakes, which partly added nutrients to the lake, which is a good thing for the phytoplankton, but then it also created kind of sediment-laden water, which reduced the amount of light to the organisms. So it was sort of a, you know, wasn't sure if this was good or bad because they got less light, but they had more nutrients. So maybe it was a zero-sum game.
Yeah.
But sediment on the glaciers changed a lot, and I think we're still seeing the response
Which
of that.
would be more melting.
Which would be more melting, because what happened was during that big melt year, the surface of the glacier, in a sense, was just melted off, revealing a lot of the sediment that was in the ice. Now it's sitting on top of the surface.
Wow.
Next year comes along, and that melts in a little bit more and increases the melt compared to a normal year when you wouldn't have that process.
Right.
So it's these kind of funny feedback mechanisms that we wouldn't have anticipated. So that's a nice thing about a long-term project.
What you mentioned forcings, now my understanding of forcings is like a volcano or what's been happening with CO2 in the atmosphere. Are forcings in the case of the Dry Valleys project and the Antarctic projects, is that melt or?
Well, it could be.
It could be anything.
Yeah, well, but it depends on where you are, right?
Okay.
If you're a stream, you're being forced by the glacier. If you're the glacier, you might be forced by the weather. But since we try to take a holistic view of this, of the situation, our forcing essentially is the weather, which affects the glaciers and then the stream flow in the lakes. And then another one actually are the katabatic winds. Not only because of the weather, but it also blows a lot of the sediment around the valleys, which help melt the ice on the lakes because it gets on the lakes, helps melt the glaciers, and it also helps to transport biological organisms through the valley. So whereas we might have separate